The behavior of a function on an interval or at a point can sometimes be inferred from its derivatives. This is helpful in finding minima and maxima for known functions and for understanding an unknown function when only its derivatives are available. To start thinking about this, let's consider the function 1 over the natural log of x and its plot from x equal 1 to x equal 2. The value of this function declines as x increases. When a function does this on an interval, we call it a decreasing function. Let's see if we can relate this to the function's first derivative. Recall that the derivative of a function at a particular point is the slope of the straight line tangent to the function at that point. Examining the derivative of this function at a series of points shows that the slope is always negative, meaning the derivative of the function is negative on this interval. Whenever a function is decreasing on an interval, the first derivative of the function will be negative on that interval. Likewise, if the first derivative of a function is negative on an interval, you can be assured that the function is decreasing. The function f of x equals the natural log of x, on the other hand, increases as x increases between 1 and 9. We call this an increasing function on this interval. If we examine the derivative of this function at a series of points along the x-axis, we see that they are always positive in this interval. Whenever a function is increasing on an interval, the first derivative of the function will be positive on that interval. Likewise, if the first derivative of a function is positive on an interval, you can be assured that the function is increasing. So what happens when a function decreases on an interval but then increases on an adjacent interval? The function x squared on the interval -2 to +2 is an excellent example. At values of x less than 0, the derivative of the function is negative, which means the function is decreasing for x less than 0. For values of x larger than 0, the derivative is positive, which means the function is increasing there. Between these two adjacent intervals at x equals 0, the slope of the straight line tangent to x squared goes to 0, which means the derivative is 0 at x equals 0. This is the value of x at which the function changes from decreasing on the left to increasing on the right. At this one point where these two regions meet, the function is neither increasing nor decreasing. The values of x at which the first derivative is 0 are called critical points. Sometimes critical points are called stationary points because the function is literally stationary at these points. Assuming the function and its first derivative are continuous, critical points will always occur at values of x where a decreasing function changes to an increasing function or where an increasing function changes to a decreasing function. These are not the only places critical points can be found, however. Let's look at a plot of the function x cubed from -2 to +2. At values of x less than 0, the derivative is positive, and so the function is increasing in that region. At x equals 0, the derivative is 0, indicating that it is a critical point. But notice that as x continues to increase, the derivative continues to be positive, indicating an increasing function for x greater than 0. Here we see that it is possible to have critical points between two intervals on which the function is increasing. Although not shown, it is also possible to have critical points between two intervals on which the function is decreasing. No matter how they arise, critical points can always be found by identifying the values of x for which the first derivative of the function equals 0. So let's see if we can do this. Finding critical points graphically is cumbersome and can be error-prone if the stationary points do not stand out clearly from the rest of the function. A more systematic procedure for finding critical points is to take the first derivative of the function, set the first derivative equal to 0, and solve for the values of x that make the derivative 0. Let's consider the function x cubed. To find its critical points, we write down the function, find its first derivative, which is 3x squared. We then set that equal to 0 and solve for x. The only value of x that makes 3x squared equal to 0 is in fact 0. The function x cubed therefore possesses a critical point at x equals 0. That's the same result we obtained graphically. A slightly more interesting function is sine x. To find its critical points, we write down the function, find its first derivative, which is cosine x. We then set this equal to 0 and solve for the values of x that make this 0. Cosine x is equal to 0 at pi over 2, but because the function is periodic, it is also 0 at 3 pi over 2, 5 pi over 2, and so on. The most general way to express these critical points is as n pi over 2, with n being an odd integer, 1, 3, 5, and so on. The function sine x therefore has a critical point at pi over 2, and every x coordinate that is an integer multiple of pi away from pi over 2. Let's consider one last example. Let's find the critical points for x squared times e to the minus 3x. Write the function first and then find its first derivative. Using the product and chain rules, we obtain x squared times the exponential times minus 3, which is the derivative of the argument to the exponential, plus the exponential times 2x. That's ugly as written, so let's rearrange the terms a bit to make it more pleasing. The first derivative is minus 3x squared times e to the minus 3x plus 2x times the exponential again. We now set this equal to 0 to solve for x. The exponential term can never make the derivative equal to 0 for a finite value of x, and because it appears in both terms, we can conveniently divide it out, leaving 0 equals negative 3x squared plus 2x. Factoring out one of the x's gives 0 equals x times the quantity negative 3x plus 2. If either one of these quantities, x or the quantity in parentheses, equals 0, the entire expression will be equal to 0. Therefore, x equals 0 is a critical point. The quantity in parentheses can be made equal to 0 by setting x equal to 2/3. This is also a critical point. We can confirm that these results are reasonable by examining a plot of this function from x equal negative 0.5 to positive 1.5. The critical points we have found are clearly the same as the points at which the straight line tangents to the function have a slope of 0. And that's critical points.